Alright, good morning everyone. We're Team 4, and today we're going to be talking to you about the Arduino platform. Our team members include Scott Friedman, our team manager, myself, Nate Hyde, the lab coordinator, Addie Matthew, the document prep, Peter Osium, the webmaster, and Young Zhao Yu, the presentation prep. We're going to start today with a quick overview of what we plan to cover. We're going to start first with some Arduino history and take a look at some of the key projects that led up to the Arduino platform. Next, we're going to look at the microcontrollers that are used on the Arduino boards. Next, we're going to look at some Arduino hardware and look at some of the various boards that are on the market today. Next, we're going to look at Arduino's IDE. And then finally, we're going to look at graphical user interface design and processing. And we're going to wrap that up with an actual live demo for you guys. Then after that, we're going to summarize it all and take any questions. So first off, what is Arduino? For anyone who's not familiar, it's an open source electronics prototyping platform. This provides a flexible interface for people to integrate project ideas that they have at a low cost. The software available is, well, it's free for PC, Mac, or Linux, and they have low cost boards. They also have the support of a lot of third-party developers, and they actually come up with like sensors and different adapters, and they have plug-and-play capabilities with the Arduino platform. So next, we're going to look at the first key project that kind of led up to Arduino. Design by Numbers, it was a project or a study done throughout the 1990s at MIT, and the goal basically was to get more people to start computer programming. This was done in a couple of key ways. First off, they simplified the programming language, and this got rid of a lot of the complicated commands that might confuse people, but it also kind of lowered the ceiling for the complexity of your applications. The other way that this was done was using visual cues. As you can see, as you program, you can see what's going on in a graphics interface next to it, and this helped people get more of an insight into how their programming is working. This inspired a number of projects, but the next one we're going to talk about is called processing. So processing, it followed in the footsteps of Design by Numbers in that it wanted to introduce programming in a visual context. And so it used a programming language based on Java, and they actually included commands like, say, ellipse or like line, and they pretty much tell you exactly what they do. And using these commands, you can make sketches or animations or interactions, and they're displayed in the graphics model next to the IDE here. And Addie's actually going to show you how some of those work firsthand in the demo later on. This was the IDE that Arduino based their model off of, and it also inspired the next project, which is called wiring. What wiring wanted to do was basically extend what processing had developed and be able to control a microcontroller with it. So using compatible sensors, you can kind of sense the environment with the microcontroller, and then the microcontroller can make decisions based on that. So say you have a motion sensor in a room and you want it to turn on, you want your microcontroller to turn on a light when somebody walks in the room. So wiring wanted to make this possible. The IDE was inspired by processing, but they actually changed the language to be something closer to C++. And so the functionality of wiring is probably closest to that of the current Arduino technology. And it was about in 2005 when Arduino came about. And this is when a couple Italian designers, they wanted a cheap way to develop projects for students. And so they used the language that was based off of wiring, and they used the IDE based off of processing. And then they started making these low-cost development boards that people could use. They're flexible, easy to use, low cost, and there's a lot of models available. And they also use kind of a familiar design between different board models, so if you switch from one to the other, you kind of have some comfort level already working with it. And using these Arduino boards, people have come up with pretty much anything you can imagine. You have things like a wall-following robot, guitar pedal, or even this laser harp. So next I'm going to pass it over to Young Zhao, and she's going to actually talk about the microcontroller chips they use on their boards.
Thanks, Nate. Hi everyone, I'm Young Zhao. I will talk about the microcontrollers on the Arduino prototyping platform. The microcontrollers that are used in the... Sorry. So the microcontrollers that are used in the Arduino platform, like in other boards, it's used the same family chip called Atmel 80 Mega series microcontrollers. They are 8-bit processors, meaning that they can access 8 bits of data in a single machine level, command. And they have that is they have their data bus in 8 bits wide. And next, I will talk about like the list of the main components in the microcontrollers. The first one is the flash memory, meaning like how much code we can write into a microcontrollers. And RAM, which pretty much functions the same as a normal PC RAM. And for the 80 mega microcontrollers, most of their analog input signals, they have like more than 10 channels and one 8-bit analog to input converters, so that any analog input signals will be converted into numbers and
Closer to the screen, you're out of the frame.
Young Joe.
Yeah, come back, yeah.
I'm sorry.
Just right outside of the light, right there. Perfect. Thank you.
So that any analog input signals will be converted to digital numbers that could be understood by the Arduino board. So as we all learn in quality Minilab, that number could be calculated by taking the analog input voltage divided by the reference voltage times 2 raised by 10. That will give us a number we will be working on with Arduino board. And digital input and output pins are the pins we will eventually implement our hardware tasks like LED flashing. For the programming, the only language that the 80 mega microcontrollers use is the AVR language. So any other codes wrote by a different language will be implemented, will be converted to the microcontroller back to the AVR language. Next, I will talk about how the microcontrollers are functions in the Arduino board. First, any analog input pins will be, any analog input signals like voltage signals will be converted to a digital understand number for the Arduino board. With a 10-bit resolution, so that means like any number between 0 and 1024 will be the number. And next, users will program their codes on the Arduino IDE, which is a programming environment for the Arduino board. And at the meantime, all the commands will be executed and stored in the flash memory in the microcontroller. And finally, the hardware. Finally, the last step is when the hardware is coded with, is modified with the codes through digital pins, and then all our final hardware tasks like mouse over control and keyboard control will be accomplished. And then, like Nate had said in the introduction, Arduino is just a prototyping platform, so in order to put it into actual design use, we need to know how the microcontrollers are wired into the Arduino input. There's a schematic that we could use, and this will tell us all the information we need to do that, and we can find this on in the Arduino website. Next, I will pass it on to Scott, who will talk about the where we put the microcontroller stuff.
Thank you, Joe. My name is Scott Friedman. I'm the project manager for Team 4. So, talking about a couple of the Arduino models that are out today, each of them kind of use the same IDE, like Nate was saying, and they all use the same microchips that Young Joe was talking about, but they all have different uses. So, for the Arduino Duo, is their newest and most powerful chip on the market right now. It has over 50 digital input-output pins, so if you're doing a huge project, that board actually might be good for you. We're actually using the Arduino Leonardo, which we'll get to in a little bit, but the Arduino Uno is actually one of the first models that they actually implemented Arduino 1.0 in the processing software, and it's still a pretty good chip and still on the market. A couple of other notable chips out there, boards, The Arduino FIO is pretty cool because it's actually meant for wireless communications. It has an XB chip that allows for any wireless sketching or wireless control that you may have in your applications. My personal favorite is the Arduino LilyPad. It's kind of cool because it's actually meant to be sewn in to applications like e-textiles, clothing, stuff like that. It's meant to be wearable. So if you want to have your shirts or something light up like Tron, that might be good for you if you're trying to do that thing. So like I said, we're using the Arduino Leonardo for our project this semester. We have about 20 digital input-output pins, 7 of which are pulse width modulation. Like Jeff said, we're using that 18 mega microcontroller. And the cool thing is it's USB connectivity, but the USB connectivity will supply a 5-volt power source to the Leonardo. But if that's not enough, if we need to actually use an external power source, it has a 7 to 12 volt that we can use as well. So some of the other benefits of the Leonardo that we can talk about is because of that USB communication and processing is on a single chip, you have extensive mouse and keyboard functionality where a lot of the libraries that you'll see for this Arduino platform is that it'll behave kind of like a USB mouse or a USB keyboard when you actually put it into the computer. Like Nate said previously, Arduino was meant for it to be low cost. For about $25 you could get your hands on a prototyping board that you can do pretty much any project you pick up. For our project in particular, the small size was really nice at 2.7 by 2.1 inches. For those who have projects that maybe packaging might not be ideal, a smaller size microchip and microcontroller might be what you're looking for. Like Nate said earlier also, common shield designs for the various applications of Arduinos. Third-party applications will create these boards that will sit directly on top of the Arduinos, and that's actually what they call a shield. So anything from maybe a guitar pedal shield to a wireless motion controller shield, those things are actually developed by Arduino itself or a third party. With that, I will hand it over to Pete, and he'll talk about the IDE.
Great. Thank you, Scott. I will be talking about the IDE, as Scott said. We'll be shifting gears here and talk to you a little bit about some software too. A couple points I want to get across with the IDE is that it's been around for a little while. It's pretty stable. There's a pretty good base, as Scott showed. There are a decent amount of Arduinos available to work with too. It's entirely open source, so the GUI can be changed. Libraries, a lot of libraries are created by users that can be downloaded, and people build upon those. And as you see here, here's a sketch, which is basically a program. And there are a couple things up at the top that basically allow you to verify the code. And then the next one would verify the code, then send it to the Arduino. And then there is a new file, save, and open. And we actually have a little demo here available, just to show you guys what it's doing. That code is just having this LED flash on and off. And if we go to the next slide, we can talk a little bit more about the syntax. For every sketch, there is a setup loop, which the user would define the pins that they would program to. In our case, we use 13. And they can set whether or not it's an output, an input, any other parameters they want to work with too. And then the loop is where the heart of the code is. That's telling the thing to turn on and off just through a single line of code, which is really nice to have since the IDE takes care of the mapping of the pins. And through the libraries, as you kind of see the LEDs flashing, but there are more comprehensive libraries out there that can support things such as servo, USB mouse, USB keyboard, and a joystick. Starting with the servo library would allow for controlling any servo, any actuator, anything like that by using pulse width modulation. The Arduino keeps track of varying the voltage for the attached motor or whatever it might be, and it can control the speed by selecting a lower voltage, higher voltage, whatever it wants, between 0 and 5 typically on Arduinos, some 3.3 volts as well. Let's see, also the mouse library is HID, which plug and play support. The keyboard. The mouse allows for very similar functionality as you see with the line here. You can tell it to do some sort of movement when it sees some various input. That way you don't have to keep track of every single time you want the mouse to move. The Arduino keeps track of that. Same for the keyboard. The keyboard allows for anything you would see on a standard keyboard as input. It also allows for the use of modifier keys, which are keys that require multiple key presses to get some extra characters you don't typically see on a keyboard. Both those libraries are pretty good for implementing a joystick. The joystick can be used by the mouse for the movement, and the keyboard can be used for keystroke input that might be on the joystick. This all can be achieved through GUI assistance too, which Addy will now further elaborate on.
Thank you, Pete. Hello everyone, I'm Addy, and I'm going to share with you some of the principles and logic behind designing a graphical user interface or a user interface. Now, as long as your project has a user or a targeted user base, you need an interface. It could be software-based or hardware or a mix of both, but you need something that your user is going to interact with, that he's going to touch, feel, see, or hear to get the job, what he wanted your project for. So there's two ways of looking at such a task. One from the end user's perspective, your customer, and one from your perspective, the developer. Now for your user, you want the output to be simple, easy to understand, and intuitive. If you have a button, be it a button on your end product or a button in your GUI, your graphical user interface, you want it to be obvious or at least hint at what it's going to do when he clicks the button. And if it's not clickable, you want to make it even more clear why he cannot click it. Now as a developer, you want complete control over your program. You wanted to give your customer exactly what he wanted, and efficiently at that. To do that, you need to take away some privileges from him and do tasks like mundane tasks like remembering numbers and variables. You don't want him to have to remember a number just to make your program work the way it should. So, with that being said, for our project, we chose the language Nate already mentioned to get our task done. Processing. It's visual programming, it's Java-based, and it's simple to understand. So without further ado, watch the screen. I'm going to show you how processing works. So as you can see, as Pete mentioned, it's a simple IDE, text editor based, syntax highlighting. And let's go ahead and start with one of the default functions. It's very similar to the Arduino IDE, so you have two functions, a setup, in which you set up your variables and things that you'll use later in the program. This function runs exactly once. Then you have a looping function, just like the Arduino, only in this case it's called draw, because you're drawing something. You need these two functions in your program. Without these, your program will give you a compile time error. However, processing is an object-oriented program. You can do anything you can do with C++ or Java. It's object-oriented. So let's go ahead and create a variable, say here. Or before that, let's think about what we want to do. Suppose, hypothetically, your customer wants you to create a window with a rectangle that moves across it. Just suppose. So the first thing you want is a window to display that. So let's go ahead and create a window here of size 400 by 400 pixels. As you can see, the syntax is very similar to C++ or Java. So you created a window using the size command. Let's save it. And now you want to create your rectangle. Processing does that for you in one command. Correct? And let's go to execute there. Now before you want your rectangle, you want it to have dimensions and an x and y coordinate on your window. So let's use variables. Integer, call it rx, x coordinates of your rectangle, let's say 20, ry, y coordinates, say 20, and execution. Now let's go back to the rect function and put in some arguments. So let's put rx there, our y, and say we want it to be a square, so a height of 20 pixels and a width of 20 pixels. And we save it and run. Let's see what processing does. Well, you have a rectangle now, but it's just sitting there. Your project, your customer wanted you to make it move. So, as I said, the draw function continually loops. It's going on, going in a loop. So, we want to make use of that. So we create a change in position, call it d, of 2 pixels with each refresh. We have one more command here after this. Say, make it move along the x-axis, so update the x-coordinate with rx equals rx plus d, execute. Let's save and see what happens now. Now if you notice, your rectangle is now moving, but it's not refreshing the movement. It's showing the previous drawn rectangle right behind it, or square in this case. So we want to remove that. And to remove that, you need a new background each time the loop runs. So what do? Redo the background each time the loop runs. Background, let's put in an RGB color here, my favorite, 255, 204, and 0. Let's see what it does. You have yellow, and you have your moving square now. Project's complete, you submitted it, your customer wants something different. He wants you to make the box or square move along with your mouse. So guess what? Processing does that for you with 2 commands, inbuilt commands. So let's change this. We don't want it moving, so we comment that out. And use an inbuilt command here, mouse x. So it'll follow your mouse's x coordinates and your mouse's y coordinates. And let's save and see what it does now. There you go, it follows your mouse. No imported libraries, no imported 3D graphics engine, nothing, just processing. Now, suppose you want to export your program. You don't want to submit code as your final project. So, let's clean it up and add one more inbuilt function, display width. So whatever, no matter what computer, whether it's 10 years old and has a display resolution of 800 by 600, it's going to take his display resolution and his heights and widths and divide it by 2 and put it in a window for him. And let's save and see what it does now. Bigger window, moving square. Now you want to submit it, this is how easy processing is. All you do is export, and you have a window now, and your program can be submitted. Alright, and with that, I'll hand it over to Nate to show us a short summary of what we talked to you today.
Alright, thanks, Eddie. So let's just take a look at what we covered today. Started with a timeline of Arduino, took a look at the key projects that led up to it. This was design by numbers, processing, and wiring. Next, we took a look at the chipset that's used in the Arduino platform, the 18 Mega series microcontrollers. Next, we took a look at the various boards that are on the market right now and some of the advantages that each of them have. Next, we took a look at Arduino's IDE, kind of how it all looks and how it's going to function for you. And then finally, we took a look at graphic user interface options and using processing to actually make some visual interactions on screen. And so with that, we'll open up for any questions that anyone has.
Did you guys look into the Texas Instruments chips at all, like the MSP430 or Stellaris? And if you did, why did you choose the Arduino?
Well, you can obviously do, as Youngja mentioned, you can obviously use any microchip to get the job done.
Right.
But the reason we went with the Arduino is you don't have to bother about creating your own schematic just to light an LED. You don't have to bother connecting capacitors and resistors just to get your microprocessor to do simple tasks. Here with the Arduino, or wiring if we wanted to, we could just plug and play. We just plug it into the USB, because USB functionality is one of our prime goals.
Mm-hmm.
So we wanted to just work with the USB straight off the bat. With just a microchip, we'd have to implement that from scratch. That involves, creating a driver, firmware, all that stuff to work with a microcontroller. Whereas with the Arduino or wiring, it's just already there.
Actually, the 430 and Stellaris are pre-packaged things, just like the Arduino thing. But I was just curious. I feel like this would be much better graphically if you're actually using the GUI.
Well, that's another reason we went with Arduino and processing is because they work very well together.
Mm-hmm.
Same language, same IDE. You can control Arduinos from the processing IDE using an inbuilt library called Firmata.
Okay.
So these things, they just work really well together, and we know it, so we just went with
I was just curious because we went through the same debate and also ended up with Arduino.
So when comparing a PIC and an Arduino, which would you say is more versatile and which one is easier to program?
Well, you can't compare the two because the Arduino uses the Atmel microprocessor. You can compare the Atmel 80 Mega series to a PIC, say. But the reason we went with the Arduino is it's already ready made. Like you don't have to put a PIC microcontroller in and buy their their interfacing for the USB or serial programming on the computer. It's just inbuilt USB, and like Yunjao said, for the Arduinos, they're cheap. They're cheaper than wiring, and they just work out straight out of the box for anything you want.
Right. Any other questions? All right, thanks.